Beneath the algorithms of cryptography lies a landscape of number patterns. This video explores a few of these number patterns. The numbers are part of the fundamental calculations used in RSA cryptography. They revolve around semiprimes, that is, numbers that are the product of two primes. They form patterns that can be viewed in the divisor plot. We will explore these numbers in the form of a bit array puzzle to find the secret primes of a given semiprime. The two prime factors of a semiprime n are typically called p and q. For instance, the number 35 is the product of primes 5 and 7. In this very small example, we can see these numbers in a single view. But when we try to look at a larger semiprime, like 143, the product of 11 and 13, it becomes more difficult to see them all on the number line. So let's plot the primes on a perpendicular axis beneath the number line and oriented downwards so that larger numbers are lower. Let's call this the divisor line. There are some important numbers that can be derived from p and q. One of them is the sum of p and q, called s. As you would expect, s is lower on the divisor line than p and q. Euler's totient function measures a special divisibility characteristic of an integer in terms of how many smaller numbers are coprime to it. The totient is important in RSA for unlocking the semiprime. The totient can be calculated as p minus 1 times q minus 1, but we can also calculate it as n plus 1 minus s. Take the semiprime 2773, the product of 47 and 59. Its totient is 2668. Let's plot this on the number line to the left of n. Notice that the distance from the totient to n on the number line is almost the same as the distance from n to s on the divisor line. This provides us with a square window to see these variables in a single view. The midpoint. This variable is simply s over 2. It sits exactly between p and q. The gap. This is just q minus p, the absolute distance between the primes. The half gap. This is just half of the gap. It will be used in a bit. The discriminant. If you know the semiprime n, and you also happen to know the sum s, then you can extract the two prime factors. This can be done with the discriminant using the calculations shown here. Arranging these values on the vertical divisor line permits us to see a connection in the context of parabolas in the divisor plot. The divisor plot shows the divisors or factors of all integers plotted along an axis perpendicular to the number line. The parabolas are curious patterns associated with the roots of numbers. Take the example of 100. We can see its divisors as a dribble beneath it. They come in pairs, and the square root is 10. Just to the left of that is the divisor pair 9 and 11. Its product is 99. And to the left of that is the divisor pair 8 and 12, whose product is 96, and so on. Now each of these divisor pairs sum to 20, and that is the order of the parabola. The number 51 is a semiprime with divisors 3 and 17. They sum to 20, and so they are members of this parabola. The midpoint of the primes is 10. Let's take that number and slide it over to the vertex of the parabola. Now we can see how some of these numbers we just explored relate to this parabola. The distance from 51 to 100 is 49, which is 7 squared. Specifically, it is the square of the half gap as expressed with this equation. Every pair of divisors can be found above and below the square root boundary, except for the roots of perfect squares, which lie on the boundary. In RSA cryptography, the prime factors should have a distance from each other that makes it difficult to crack the code. If they are too close to each other, in other words, too close to the square root of n, then it would be too easy for someone to find them. Likewise, if they are too far apart, causing one of them to be small, then it would be too easy for someone to find them. They must be balanced. Now let's explore some of these variables as bit arrays by converting their decimal representations into binary. This breaks a number down into its simplest building blocks and makes some underlying patterns more apparent. For instance, a number and its double, the number multiplied by 2, may look quite different in decimal, but in binary, the double is identical except all the bits are shifted leftward by 1. In binary, operations feel more mechanical. Could the binary representation help us to see and manipulate these patterns? As we saw before, if you happen to know the value of S, then you can find the primes. With this bit array puzzle, we will fill in some of the bits based on prior knowledge about the math. Step 0, we start with 4 rows of unknown bits. Step 1, we fill the first row with the bits of the known semiprime n. We'll use this semiprime as our example. It's a little over 100 million. Step 2, we will fill row 4 with the value n plus 1. This can be used to calculate the totient. Step 3, since p and q are both odd primes, we know that p minus 1 and q minus 1 are both even. The product of two even numbers is always a number that is divisible by 4. So let's set the last 2 bits of the totient to 0. Step 4, we set the last bit of S to 0 because we know it is always even, being the sum of 2 odd primes. Step 5. In a very large semiprime used in RSA, the totient is close to n relative to the size of n. The primes are chosen to be similar in size, which means they are also relatively close to the square root of n. Now, in the binary representation of a number, its square root takes up approximately half the number of bits as the number. Twice the square root takes up a little bit more. As a heuristic, let's assume that since n and its totient are close, the leftmost bits are the same. So let's copy a little less than the first half of the leading bits of n to the totient. Step 6. We know that S is much smaller than n. It is approximately twice the square root of n. So let's set the first half of its bits to 0. And to be safe, we'll go with a little less than half. Step 7. Now we have a bunch of unknown bits that need to be filled. With sufficiently small semiprimes, there are ways to fill in the missing bits in a reasonable amount of time. As an exercise, here's one brute force solution. We'll arbitrarily set S to twice the square root of n as a start. We will truncate it to an integer, and if it's odd, we'll add 1 to make it even. From this arbitrarily low value of S, we will repeatedly increment it by 2, each time using its value to calculate a new discriminant. If that new discriminant is a perfect square, then we are done. We know we are able to extract the primes. And since we now have the value of S, we can calculate the remaining of the totient and fill in the bits. There are probably more elegant and efficient ways to fill in the extra bits, especially if we have to deal with large semiprimes. Are there any hidden patterns that we humans are not able to pick up? Could AI be used to see, in some sense, other patterns that could inspire new steps to add to this puzzle? Whatever the future holds, we hope this video provides some insight into the patterns of semiprime factorization and a better appreciation for math using visual illustration.